Hello everyone, welcome to AP Chemistry Unit 1. Let's begin with the first subtopic, the periodic table. So the periodic table contains all 118 elements that you will need to know for the exam. Let's talk about what each individual box means and how we can use this data in chemical equations. So each letter in each different box is the elemental symbol. So for example, carbon's symbol is C, and it can be used interchangeably with the name of the element. In chemical formulas, carbon will be written shorthand as C. Next is the atomic number. Each element's atomic number tells us how many protons the element's nucleus has. This will also be the number of electrons surrounding the nucleus if the atom is neutrally charged. Lastly, we have the atomic mass. Carbon's atomic mass is 12.01 AMUs, or atomic mass units. This is the average atomic mass of every carbon atom, and it is also the molar mass, meaning that 1 mole of carbon weighs 12.01 grams. In reality, there are many forms of carbon, such as carbon-12, carbon-13, carbon-14, etc. Now, it's important to understand what the mass number actually represents. For carbon, its mass number of 12.01 represents the average mass of all the carbon atoms in the universe. The average mass of all of carbon's different isotopes is 12.01. Isotopes are atoms of an element with different numbers of neutrons. While all isotopes maintain the same number of protons, notated by the atomic number, they differ in number of neutrons, which in the end changes their mass number. The periodic table also has rows called periods. The vertical columns of the periodic table are called groups. The periodic table has 18 groups. Group 1 is known as the alkali metals. Group 2 is known as the alkali earth metals. Groups 3 to 12 are known as the transition metals. Groups 13 to 16 are composed of many different groups. Group 17 is known as the halogens, and Group 18 is known as the noble gases. Next, let's talk about moles. So a mole is just a quantity that represents 6.022 times 10 to the 23rd atoms. And yes, that number is important. It's known as Avogadro's number. We also talked about molar mass, which is why that moles is equal to grams over molar mass. For example, carbon's molar mass of 12.01 means that there are 12.01 grams of carbon per mole. So 1 mole of carbon equals 12.01 grams. There's an equation called the ideal gas law, which relates moles to pressure, volume, the gas constant, and temperature. This equation is only true when analyzing gases. We can now relate pressure, volume, temperature, and moles. Keep in mind that R, the gas constant, is equal to 0.0821. Another important formula for gases specifically is that 1 mole of gas equals 22.4 liters. This is true for all gases. There's also something called molarity. Molarity expresses the concentration of a solution in terms of volume. M, which stands for molarity, equals moles of solute over liters of solution. So molarity represents the amount of moles of something per liter. Now we can use what we just learned about moles to begin learning percent composition. Percent composition is the percentage of mass that each element has in a particular compound. It is found by dividing the mass of each element or component of the compound by the total mass of the compound. So let's calculate the percent composition for CO2. We already know that we have 1 mole of carbon per mole of CO2. This is because carbon has a subscript of 1. We also know, by looking at carbon's molar mass, that there are 12.01 grams of carbon per mole. We can divide this by the molar mass of CO2, and we can add up the molar masses of all the individual elements. Since we have one carbon atom and two oxygen atoms, we can add the molar mass of carbon plus 2 times the molar mass of oxygen to find the molar mass of CO2. And we found that CO2's molar mass is 44.01 grams. And so now we can plug this into our calculator to solve for the percent composition of carbon. And we get about 27.3%. We can repeat this process to find the percent composition of oxygen. We get about 72.7%. Check out my video on percent composition if you're still confused. Linked in the description below. We can also use percent composition to find empirical and molecular formulas. Here's an example problem. So let's say we have a compound that we have found to contain 56.5% carbon, 7.11% hydrogen, and 36.4% phosphorus. How can we find the empirical formula of this compound? Well, first we want to assume a 100 gram sample. This would mean that if we have 56.5% carbon of a 100 gram sample, we would have 56.5 grams. Same with hydrogen with 7.1 grams and 36.4 grams of phosphorus. Now, we can divide these masses by the molar mass to find the number of moles. Now we've solved for the moles of carbon, moles of hydrogen, and moles of phosphorus. We then divide each of these mole values by the lowest of the values. We've now found the values that are going to correspond with the empirical formula. In this case, this compound's empirical formula will be C4H6P. This is how you go from percent composition to empirical formula. But we're not done. There's also something called molecular formulas. Think of this empirical formula as like a simplified version that we may use to actually determine the molecular formula of the compound. So if we're given that the compound has a molar mass of 170.14 grams per mole, we can now solve for the molecular formula. The first step is to find the molar mass of the empirical formula, and we find it to be about 85.07 grams per mole. We now divide our given molar mass by our empirical formula's molar mass, and we get 2. This means that our molecular formula will have subscripts that are 2 times as large as the empirical formula. So if our empirical formula is C4H6P, then our molecular formula will be C8H12P2. If you want to learn more about empirical and molecular formulas, check out my additional video in the description. Lastly, let's talk about Coulomb's law. Coulomb's law discusses the relationship between the electrostatic force between the nucleus and an electron with the magnitude of the positive charge, the negative charge, and the distance between the charges. On the AP Chemistry exam, you will not be required to use Coulomb's law mathematically to calculate any forces. However, you should be able to understand the relationship between forces, magnitude of charges, and radius. As the charges increase, the strength of force between them also increases, since the charges are in the numerator. If the radius were to increase between the charges, then the strength of the force would decrease, because the radius is in the denominator. Keep in mind that since radius is squared here, if you were to increase the radius by a factor of 2, the strength of the force would decrease by a factor of 4. This is due to the inverse square law. Let's look at some review questions. Pause the video if you want to try to solve this one on your own. So to find the percent composition of carbon in this sample, we first have to find the mass of carbon. Since there are 2 carbon atoms in this compound, we're going to take 2 times the molar mass of carbon over the molar mass of the entire compound, which will be 2 times the molar mass of carbon plus 3 times the molar mass of hydrogen plus 2 times the molar mass of oxygen. And so we find the percent composition of carbon to be about 40.7%. Now to find the number of hydrogen atoms in a 75 gram sample of this compound, let's start by finding hydrogen's percent composition. So in this compound, we find hydrogen's percent composition to be about 5.1%. We can now multiply hydrogen's percent composition by the mass of the sample. And we find that there are about 3.85 grams of hydrogen in the sample. Now, we can convert from grams to moles and then moles to atoms. To convert from grams to moles, we can divide by the molar mass of hydrogen, which is 1.01 grams. To convert from moles to atoms, we can multiply by Avogadro's number. Now we can plug this in our calculator to find the number of hydrogen atoms. And we find that there is 2.30 times 10 to the 24 atoms of hydrogen. Let's look at another review problem. Part A says to find the pressure in atmospheres of 0.05 moles nitrogen gas in a 750 milliliter container at room temperature. We know the equation moles equals PV over RT. We're given moles, volume, and temperature, and we know R is a constant, so we can solve for pressure. And we have to be careful here. We can't plug in milliliters because the equation requires liters, so we have to convert from 750 milliliters to 0.75 liters. We also have to convert Celsius to Kelvin, and we can do this by adding 273.15. Using algebra, we can solve for pressure. And we find pressure to be 1.60 atm. Part B asks us to find the mass in grams of the sample of nitrogen gas, which has a chemical formula of N2. Since we already have the moles of the sample, we can convert this to grams by multiplying by the molar mass, and we find that the sample of nitrogen gas is 1.4 grams. Let's look at another problem. This next problem asks us to order the following Coulombic attractions from strongest to weakest. I've written Coulomb's law, which is force equals charge 1 times charge 2 over radius squared. Let's start off by looking at A. Before doing any math, let's see if we can qualitatively analyze this problem. Let's let A be our control group. So we'll let this force equal N. For B, if we double the radius, this will mean that the force will be decreased by a factor of 4 due to the inverse square law. This means that the force in B would be N over 4. If we double one of the charges but keep the radius the same, this would double the force. So C would be 2N. And lastly, if we double one of the charges, we will double the force. But if we double the radius, that will also decrease the force by a factor of 4. So we get 2N over 4, which is equal to N over 2. So from strongest to weakest, this would be C, A, D, and B. Let's look at another problem. This next problem asks us to classify the following elements into their correct groups. As long as we know what the names of the different groups in the periodic table, we can do this very easily. Since chromium is in group 6, it would be a transition metal. Since potassium is in group 1, it's an alkali metal. Since bromine is in group 17, it's a halogen. Since magnesium is in group 2, it's an alkali earth. Since zinc is in group 12, it's another transition metal. Helium is in group 18, which means it's a noble gas. And sodium is in group 1, meaning it's an alkali metal. Let's look at one last problem. So a compound is formed to contain 83.6% carbon and 16.4% hydrogen. Let's find the empirical formula for this compound. So the first step is to assume a 100-gram sample. This means there will be 83.6 grams carbon and 16.4 grams hydrogen. We can now divide these values by their molar masses to solve for their molar values. Now that we've found the amount of moles of carbon and hydrogen, we divide both by the smallest value. It seems like we've run into a problem. While we've reduced carbon to 1, we've reduced hydrogen to 2.33, which is not a whole number, so that can't be part of an empirical formula. To deal with this, we can multiply both numbers by 3 to get rid of the fraction. And so we've now found the values for the empirical formula. We have C3H7. So now let's find the molecular formula if the compound has a molar mass of 86.17 grams per mole. We now divide this molar mass by the molar mass of the empirical formula. And this comes out to about 2. This means that to find our molecular formula, we have to multiply the subscripts of the empirical formula by 2. So our molecular formula is C6H14, known as hexane. And there we go. Thank you so much to my channel members, RealTHF and Stefano C, for your support. Make sure to donate to support the channel. Thanks for watching. Like and subscribe.